This course on chemical reaction engineering is divided in 4 competencies. The material covers the first 4 chapters of the book Chemical Reaction Engineering of H. Scott Fogler, 4th edition. The methodology to follow is to apply an algorithm or procedure through which the volume of a reactor is obtained. The steps: first, molar balance; second, reaction rate data; third, stoichiometry; and fourth, the combination of the previous 3. Some concepts that should be highlighted are: we are going to use units of mass in moles, where 1 mole contains the Avogadro's number of atoms or molecules. For example, methane has a molecular weight of 16 grams per molegram. Then the weight of 1 methane molecule will be 16 grams divided by Avogadro's numbers, which is 6.023 times 10 to the 23 molecules per molegram. This is equal to 2.65 times 10 to the minus 23 grams for each molecule of methane. So we are going to work with a lot of molecules. Another concept that we are going to use is the gas law to express concentrations in terms of pressure. If we recall the ideal gas law, it says that the pressure times the volume is equal to the number of mole times the rate, the gas constant R, times the absolute temperature T. From here, the concentration is equal to N, the number of moles, divided by the volume, which is going to be moles by liter, by example, and this is going to be equal to the pressure divided by the gas constant R times the temperature T, where P is going to be the pressure, B is going to be the volume, T is going to be the temperature, N is going to be the number of moles, and C is going to be the concentration. Another concept that we are going to use is the integral calculus and the physical meaning of the area under the curve. In our case, the flow system's reactor's volume of the 11 scale plot. So the area under the curve of the 11 scale plot is the volume of the reactor. By the end of the 4 competencies, the student will be able to obtain the volume of various reactors at constant temperature for a production line project. Although the book contains tables with the formula required to resolve different problems, where do these equations come will be explained. So at least once we are going through all the development of these formulas, knowing that the book has tables for our disposal. Competency number 1, objective. After completing this module, the student will be able to describe and define the rate of reaction, derive the general mole balance equation, and apply the general mole balance equation to the 4 most common types of industrial reactors. Tension gathering. The student will observe that although metric units are used primarily in this competency, These units could be mole pound per cubic meters or joules per mole. A variety of other units are also intentionally used, like pounds per cubic feet. Chemical reaction engineering. Chemical kinetics is the study of chemical reaction rates and reaction mechanisms. And the study of chemical reaction engineering combines the study of chemical kinetics with the reactors in which the reactions occur. After defining the rate of reaction, Ra, in this case minus Ra is because A is disappearing, a reactant that is going through a, a product, but we will use the general mole balance equation to develop the design equations for the most common industrial reactors, which are batch, continuous stirred tank, CSTR, tubular, PFR, and packet bed, PBR. The rate of reaction, RA. The rate of reaction tells us how fast a number of moles of one chemical species are being consumed to form another chemical species. The rate of disappearance of a species, say A, is the number of moles of A molecules that lose their chemical identity per unit time per unit volume. So the rate will be moles of A divided by seconds divided by liters, by example. The rate at which a given chemical reaction proceeds can be expressed in several ways. Consider the reaction A plus 2B gives C plus D. The numerical value for the rate of disappearance of A minus Ra is a positive number. Example, minus Ra could be 4 moles of A per cubic decimeters times second, where cubic decimeters is equal to liters. So here again, the rate has negative sign because A is disappearing. The rate of the reaction minus Ra is the number of moles of A, let's say chloral, reacting or disappearing per unit time per unit volume. So the rate unit will be mole of A divided by liters times second. Heterogeneous reactions involve more than one phase. The dimensions of this heterogeneous reaction rate Ra prime are the number of moles of A reacting per unit time per unit mass of catalyst. So the units of Ra prime will be mole divided by grams of catalyst times second. Here, the important is not the volume of the reactor, but the grams of the catalyst. The rate equation, example, rate law. The rate equation for Rj is an algebraic equation that is only function of the properties of the reacting materials and reaction conditions. The rate equation is independent of the type of reactor, batch or continuous flow, in which the reaction is carried out. For example, the algebraic form of the rate law for minus Ra for the reaction A goes to product might be a linear function of concentration, like minus Ra equal K, the rate constant, times the concentration of A elevated to the first power. That's why it's linear. Or, as it will be shown later, It might be other algebraic function of concentration, such as minus Ra equal K, the rate constant, times the concentration of A elevated to the second power.